Hey guys, today we're doing Chapter 10, Section 6, and this is on it's on other normal distributions, but basically we're going to talk about standardizing the variable in order to plug something into a standard normal distribution. So remember that if a variable x has a normal distribution with a mean of m and a standard deviation of s, then the transformed variable using our z-scores is just going to be x minus m over s. So we're taking our number minus the mean divided by the standard deviation, and that's going to standardize our variable so that we can use it with a standard normal curve. Z is often called the standard score or the z-score. The process of getting z is often called standardizing the variable, and we talked about all this in Chapter 3. So if I want to go from a normal distribution to a standard normal distribution, basically what I need to do is start by standardizing my variables, and then I can use my standard normal distribution table in order to estimate those probabilities. So the heights of adult males in the U.S. are approximately normally distributed with a mean of 70 and a standard deviation of 3 inches. Estimate the probability of the man shorter than 5 feet 6 inches. So I want to think about a guy being shorter than 5 foot 6 inches. So I'm looking for the probability that x is less than, and I'm going to turn this into inches because 70 and 3 are both in inches. So 5 foot 6, that's going to be 66 inches. Okay, so this is what I'm looking for. I'm looking for this probability, but I can't find it until I've standardized everything. So I'm going to start by standardizing the 66 inches. So I'm going to say 66 minus my mean divided by my standard deviation. And when I do that, I get negative 1.33. So this is going to actually be the probability that z is less than negative 1.33. So now I can actually find that probability using my table. I'm just going to start by drawing a little picture here. So at negative 1.33, I want everything less than that. Well, that's the equivalent of saying I want the complement of this area. So the way I think about this is if I were to mirror this to the other side, that would be 1.33, and the complement would be everything below 1.33. So I'm going to look for everything below 1.33, and I'm going to do the complement of that. So looking at my standard normal distribution table, this guy here, I'm going to look up 1.33, and I get 0.9082. So I've got 1 minus 0.9082. Okay, and that gives me 0.0918. So approximately 9% of people are going to be shorter than 5 foot 6 if you're male, according to this problem. Alright, let's do another problem that goes from normal to a standard normal curve. We've got a batch of light bulbs that's tested and is found to have lifetimes that are normally distributed with a mean of 1,067 hours and a standard deviation of 92 hours. If the manufacturer guarantees that the light bulbs will last for 800 hours, what is the probability that the light bulb does not meet the guaranteed lifetime length? So if I want to look for the probability that it does not meet the guaranteed lifetime length, that means that I'm looking for the probability that my x is less than 800 hours. So I'm looking for the fact that my light bulb is not even reaching 800 hours. Now this number here I need to standardize, so I'm going to take 800 minus the mean divided by the standard deviation, and that gives me negative 2.9. Okay, negative 2.90. So I can rewrite this as the probability that z is less than negative 2.90. And if I draw that out, well, I've got my negative 2.90 here, and I want everything less than that. So it's going to be a really small probability. I'm going to use the same method that I did here, thinking about that reflection and then taking the complement of it. So if I look at my table and find 2.90, I'm going to take the complement of anything that's under 2.90, which is 0.9981. And when I take 1 minus that, that gives me 0.0019. So that's approximately 2%. So approximately 2% of those light bulbs are going to fail this lifetime guarantee. Okay, the next one is going from a binomial to a normal. So you'll notice that in the other two problems they said that they can be approximated by a normal curve. Well, in this one it's saying that we are just have fewer than 20 or more than 30 heads in tosses of a fair coin. You should right away recognize the fact that when you have a fair coin, you either get a heads or a tails. That is a binomial experiment. Because remember, in a binomial experiment, we can either have a success or a failure. Those are the only types of outcomes. Okay, when going from binomial to normal, we need to perform a test before we standardize the variable. We need to make sure NP and NQ are both greater than or equal to 5 to assure that the binomial situation can be approximated with a standard normal distribution. Okay, so these situations take a little bit more work, but they're not too bad. Okay, so if I want to estimate the probability of getting fewer than 20 or more than 30 heads in 50 tosses of a fair coin, first of all, my n is 50, that's my number of trials. My probability of success is 0.5, and my probability of failure is 0.5 because I'm talking about tossing a fair coin. Okay? So, if I want to figure out the probability of getting 20 or more, or less than 20 or more than 30. Well, first thing I need to do is check to make sure that I can approximate this with a standard normal distribution. So n times p, that's going to be 50 times 0.5, which is 25. And n times q is 50 times 0.5, which is 25. So since both of these are greater than or equal to 5, I know that I can approximate this, so I can continue going on. So I'm looking for the probability that I have less than 20 or greater than 30 heads. Okay? So each of these I need to standardize using my z-scores. So that also means that I need to find the mean and the standard deviation. Well, remember that in a binomial situation, the mean is n times p, which we've already found is 25, and the standard deviation is n times p times q, the square root of that, sorry. So the square root of n times p times q in this case is 3.54. So if I'm going to standardize each of these, I'm going to take 20 minus 25 over 3.54, and then 30 minus 25 over 3.54. This one gives me negative 1.41, and this one gives me positive 1.41. So now I can rewrite these as the probability that z is less than negative 1.41, or the probability that z is greater than 1.41. Okay, so looking at my table here, or my graph, that would be like, if this is negative 1.41 and this is 1.41, I'm looking for these two areas here. So if I find just one of those areas, I can just double it, and that'll give me the overall probability. So I'm just going to look for this area here because I know that's the complement to shading everything below. So using my distribution table, I'm going to look up 1.41, which is 0.9207. And I'm going to take the complement of that, which gives me 0.0793. And then I'm going to double that, which will give me that overall area, which is 0.1586. So it's approximately 16% are going to be fewer than 20 or more than 30. So there's about a 16% chance that that will actually occur. Okay, that is everything for section 6.